So welcome. Thank you for showing up on a Saturday morning, noon for me over on the East Coast. Many thanks to Tim and colleagues of the Genealogical Forum of Oregon for the invitation. And this is fun. All new presentation. Nobody's quite asked me before about how does this all work. So anyway, you can see me on the left there. I won't say much about myself. I'm the author as far as we're concerned here of a few online tools named there. And I'll talk about briefly in particulars, but mostly it's about the methods behind them. And everything I do is free and wide open at the URL there that you see. So what's this about? It's putting SNPs on the map. It's an amazing thing. I'll jump right to second slide. One of my favorite slides of this kind of thing. This is my application, one most common application that people know about, called SNP Tracker. I started this about 4 or 5 years ago when I got into this hobby. And this, to me, is kind of a remarkable thing. We could not have imagined doing this 10 or certainly 20 years ago. What this shows are 3 SNPs, and you can see them at the very top of the screen, IBY182260 and so forth, that happen to be attached or known to 3 men who live on the Isle of Man, which is a tiny little island in the Irish Sea between Ireland and Great Britain. And because it's a small community, and I know that I've chatted with a few of them, they're very big on DNA genealogy. I'm almost certain that the guys who have these SNPs know each other. They probably live on the same street. So how in the world do we know that these 3 men living on arguably the same town, maybe the same street, know each other on this tiny island, have their fathers' paths in ancestry all the way back to our species origins in Africa 240,000 years ago? How in the world do we know that these are the paths that they took with reasonable accuracy? And it's true. This is how they got there to the Isle of Man. We couldn't have imagined doing this more than a few years ago. At best, 10, 20 years ago, you'd get a picture in a textbook or maybe an issue of National Geographic that would have big colored arrows of the great migrations of ancient humans. And that would be fine. It would be a static picture in a book. Remember books? And that would be fine. We learned something. It's rather interesting. And there'd be debates about out of Africa if you got into it. But today we can do this in detail, and most amusing, most interesting, we can do it on an individual basis. So that's the problem today, is how the heck do we draw these maps, and what are they all about? Okay. Everything I do is limited, everything in science is limited by the data you've got. So a little simple rubric here of the data's on the outside, and what data you have drives what you can do. If you don't have the data, you can't do anything. So I don't know if the metaphor, well, let's carry on. Here's my universe of data. Now around the outside rim, we have the data sources that I use for this hobby in retirement. The Haplotrees, Surnames, census data, GEDCOM files, Wikitree, STRs, short tandem repeats, archaeology and history. All of those in various mixes come together, in my mind anyway, and manifest in a few software tools. Today, we're talking about the ones in the top, SNP Tracker and a British-Irish mapper. And I won't be talking about some of the others, although maybe we could explore some of those in questions much later. They're not really relevant to today's. The point is the data here is the data drives what you can do. So here's a little outline of where we're going. And I'll start talking about data sources with some illustrations, examples in all cases. The sources of the DNA haplotrees, ancient DNA. There might be some surprises in there for you about ancient DNA. User ancestry, meaning when you sign on to, in particular, FTDNA, which is my principal source of information, because they open things up pretty well, actually. You can pick an ancestry, paternal ancestry by nation. They limit it to nationality. So you could say Irish, you could say Swedish, you could say South African or Australian or whatever you want. So that a bit of information we have. We have surnames and census, which I haven't talked about much, but there's an interesting overlap you can do with SNPs. which in certain cases gives you really lovely precision and an interesting set of stories about surnames and census data. And finally, another thing that I haven't implemented, but it occurred to me, it was something fun for me to do in the future, is to do precise location with family tree overlap. And I'll talk about how that might work. Then we'll talk about methods. For all of you who fondly remember your high school mathematics, you'll love this part, although no equations. There's a lot of math in it actually behind the scenes. How do you connect to the haplotree? Branching geometry, just plain old geometry and common sense is a big part of how you draw these diagrams. Interpolation gets into the math a bit more than anything else. Go over that somewhat briefly. Negative evidence is a very interesting thing. That's a very, not so much a computer thing, but a human thing. What do you do? What does it mean to have negative evidence? And it's very influential. We'll talk about averaging and smoothing. And finally, I don't think it's ever enough, and we can call this a science because it is. I don't think it's ever enough for a scientist just to collect a lot of stuff. I think you've got to go out on a limb now and then, and try and do some synthesis, make some observations, trying to bring stories together. Look for new things to do. Look for those ahas or those curiosities that you didn't quite expect when you were collecting all the information. And that'll be how we end this up on some fun notes. And also talk about problems that lead to really bad maps now and then. Okay, so here we are. All right. Now the big sources of data are shown in the big color blobs here. And you can see it's overlaid on a map of Eurasia and North Africa. So we'll start at the bottom right with archaeology. And this is very approximate. I'm simplifying things quite a bit, but you'll see these themes throughout the talk. I use archaeology, by which I mean just reading the literature, reading Wikipedia, reading very good websites, reading the academic literature on archaeology, trying to keep up with it, mostly for events and migration information that happened in the Paleolithic. That's the Old Stone Age. And for my part, that's mostly relevant here from Central Africa over to Southeast Asia, that broad swath, keeping it kind of oversimplified here. But that's archaeology drives a lot of that mapping. Then we move up and we move forward in time from the Stone Ages, the Paleo, the Old, the Middle, and the Neolithic Stone Ages. And across most of Eurasia, from the Black Sea all the way over to the Pacific, in a broad blue blob there, and ancient DNA comes into its fore here as a data source. I'll talk about those red circles in a second. Then moving forward in time again and over to Europe, moving west to Europe, user ancestry, what I described before, where somebody says they're Irish, says their paternal ancestry is Irish or Swedish or whatever. That becomes more relevant and more important in Europe and mostly in the Neolithic to Bronze Age. And finally, just because that's where the data are, there's no particular Anglophilia here, but I have the data and that's why I use it for Britain and Ireland. We can use surnames and census data, and particularly from the Iron Age to the modern era in the British Isles. Now, what are the red circles? The red circles, I do have a background as a quantitative scientist, so I like to see error bars on things. The red circles are the one standard deviation or one sigma uncertainties, average uncertainties for these types of data. So for ancient DNA, that great big red circle, which stretches as I happen to draw it from the Caspian, halfway out across Siberia, is the typical uncertainty in miles or kilometers, whatever you like. Tim, you okay? Shaking your head. Typical uncertainty for locating a SNP with ancient DNA. If we move over to the Neolithic Bronze Age with user ancestry, our typical red circle there is about the size of a country. You can see it's about the size of Spain or France or Italy or Germany, what have you. So that's our uncertainty with SNP location there. And when we're fortunate enough to have Anglo-Irish surname and census overlap data, we can often get it SNP location down to the scale of a couple of counties. That is a subregion, maybe half the size of Ireland, or put together a couple of large counties or the size of Wales or Scotland. We can do that when we have that kind of data. So that's a sense, right away, you're getting a sense of error bars and uncertainty here, which is a very important part of all this. I'll probably say it in several ways over and over. We do the best we can. I do the best I can. There are only a couple of sites that do this. Hunter Proven with his tools and FTDNA with our Globe Trekker tool, which came out earlier in the year, a year ago. And it's very important not to take the answers or the paths that we show terribly literally. So keep those error circles in mind. Basically, be happy with what you got. That's what the data allow us to do. And don't sweat the small stuff too much because those red circles are a big hint that the data don't really justify. All right. So the first bit of data, a brief part here is just to talk about the haplotrees. The haplotrees don't provide mapping as such, locations, nothing about geography, but they importantly give us connections between SNPs. They tell us who is related to whom, who descends from whom, and they give us dates. It's wonderful. I mostly use FTDNA, and I don't know, a year and a half ago now, they came out after a lot of discussion and background stuff that I know about with Ian MacDonald, his superb mathematics and analysis, put really excellent dates for formation and time to most recent common ancestor on the entire Y haplotree. And that is just proven invaluable. So we have the dates of events and we have connections thanks to the haplotrees. Now, let's compare the haplotrees. And I'm sorry to say, this is about the last I'll talk about mitochondrial DNA. And this slide is to tell you why. It's about data. And the Y chromosome, if you do a big Y test, what FTDNA calls their big Y test, costs, I don't know, on sale, maybe $350. They'd sequence 20 million base pairs of your Y chromosome, those of you who have a Y chromosome. If you buy a mitochondrial test and you get the full sequence test, that at most is 16,000 base pairs. The mitochondrial chromosome is simply tiny. It's a bacterial vestige from, 2 billion years ago. So there's a 1,000-fold difference in the amount of information. Actually, there's more than a 1,000-fold difference for reasons I won't go into about the mitochondrion. A 1,000-fold difference in the amount of data we have when we do Y versus mtDNA sequencing. And that's full sequencing. That's the best we can do. As a result of that, one way to express that difference is the average years between SNPs. So if I, for Y chromosome, if you do the big Y, the whole deal, you can average about 80 to 90 years between SNPs, which is to say that between me and my great-grandfather, we probably have reason to expect there will be one marker difference between us. A couple of us, I might have the same markers exactly as my father, but between my father and my grandfather, there might be a new SNP appeared. And so you get the idea, about 84 years between SNPs on average. Mitochondria, because we have so much less data, it's 7,000 years. That's, in other words, to have a likelihood of a difference between one of my mitochondrial markers and the one preceding it, I have to go to the Neolithic. In other words, everything from Roman, medieval, is invisible to mitochondria. So that's why I'm going to focus on Y-DNA. It's not about gender bias or anything. It's data bias. It's where the data are, and that's just the way the DNA is. All right. So here's another view of the haplotree. Last slide about haplotree. Today, from the FTDNA tree, which I use, it's the biggest in the world, fastest growing in the world. They're pushing 300,000 contributors. There are 44,000 branch points on this tree. It's like a family tree, of course, it's branching. And there are over 30,000 terminal SNPs or leaf SNPs at the bottom of the diagram. A rough sketch here with time on the vertical axis. We have Y atom, maybe 240,000 years ago, a little bit of branching going on, a little branching going on. We get down around 50,000 years ago, and that's when we know, and we'll talk about the mapping, why we know. This is when you get a lot of out of Africa of people who have survived. Remember, you only see survivors because only survivors can do modern DNA testing. So you get out of Africa, and then you get the branches get bigger and bigger. They get so busy on this diagram that I do them in solid color blocks because you just can't see it it makes a messy picture otherwise. You can see before out of Africa, we have some African and European branching in haplogroup E, which happens to be mine. We have some Nordic branching coming in at around 50,000 years ago, ancient pan-European and Nordic. And then when you come down to Bronze Age expansions, you can see there's an explosion, like whole half of all the Y tree is after R1b in explosions, which we can roughly speaking now attribute to Northern Europe, Germanic, Iberian, and British Isles. And we'll talk a bit about this as we go. But that's a very quick overview of the Y haplotree. All good? Okay. Now a fun one, ancient DNA. Paleolithic era is about 1,200-mile uncertainty. That's that red circle I showed you before. So here's what we've got for ancient remains. These days, it's amazing, especially labs like David Reich at Harvard and some others are in Copenhagen and Max Planck in Germany, are just powerhouses for this with clean rooms. And they've really got it down. I estimated Reich's lab does 3 or 4 whole ancient genomes every work day. That's amazing because it's a whole sequencing of ancient DNA, which is harder than modern DNA because it's a mess of fragments, and that includes all the computer work to put it together. So today we have about 10,000 whole ancient genomes, 5,500 with good Y-DNA, and 17,000 with mitochondrial DNA, and they're mostly shown here as the dots. What you don't see here is that there aren't, and that's why I don't show it, there aren't many dots in the Americas and Southern Africa. Again, it's where the data are. It's where the archaeology is. You also see the dates of the dots here. We have really nice coverage in Europe. That's no surprise. People are most interested where they live. And they have academic traditions of archaeology, and the archaeologists collaborate with the geneticists these days and so forth. So we have a lot of ancient DNA in Europe. It's quite good. We're not too bad across Asia. There's probably a lot in China, but they don't publish, or I don't read Chinese. I don't have access. That's too bad. That would be interesting. There's not much in India. There's nobody lives in Saudi or middle of Saudi Arabia, but they don't dig it up and publish. And same with Africa. So this is where the data are. It looks like a lot, but as you'll see, it's actually rather sparse. And look at the dates here. The cool colors which are the ones of interest mostly. You'll see why. Bronze, Neolithic, Mesolithic. They're kind of few and far between across Eurasia, but they're critical. We'll get into that. Ancient samples, by the way, it's a bit of a misnomer, whatever you mean by ancient. This is just the distribution. They're mostly medieval. Many are medieval. So you dig up a medieval cemetery in Hungary, that's fantastic. You get all this interesting information about the history there. You call it ancient DNA? Well, yeah, sort of. But it's maybe 1400 AD or 1500 AD, something like that. There's a lot of that. Anyway, you can see the distribution there. I'm going to keep moving along. Here's one of the problems. The assigned SNP is usually much older than the sample. Diagram on the left. Let's say there's an ancient site, and that's the skeleton. Now when we dig this up and we do the DNA, we've got to assign this guy a SNP. And what SNP do we assign him? Well, it'd be nice if we could assign, do I have a pointer that works? Can you see that, my mouse? I'm not sure. Good. It would be nice to assign him this one, which is the most recent SNP, but we don't know that. We don't know it because he's the only guy on this branch, probably. The other branches are either extinct or we haven't found their skeletons yet. So he's on his own branch. And usually, the nature of ancient DNA, it goes way back in time until we have a SNP that's part of the tree that we know. Remember, our tree, quote, our tree, is based on modern people. So to get this yellow SNP, it has to be intersecting with the trees of people men who live today and have DNA tested. But you understand, all these other branches have gone extinct, or here's a skeleton that's on the branch, but we haven't dug it up yet. We don't know about it yet. So that's why they're often thousands of years different. Another reason that assigned SNPs are often much older than the sample meaning the skeleton, is that until fairly recently, most academics used inexpensive STR or SNP pack tests. It was expensive to do a whole genome. Nobody had the technology or computer technology until the last 10 years at best. So there's a lot of literature, particularly Russia and some other and earlier archaeology, where they only used inexpensive tests. And that's why you get a lot of things like RM269, which is famous or infamous only because it was the one identified fairly early, and you'd get an inexpensive STR kit, and that's what would pop out of the software. You can see the distribution there. There's an average of 7,500 years between ancient DNA that's labeled 269 and when 269 actually appeared. Okay, so you can dig up one of those Hungarian skeletons that's in the medieval 1400 AD, a medieval Hungarian skeleton, and he'll be labeled M269. Well, I'm sorry, but M269 arose 10,000, I don't know, 9,000 years earlier in the middle of Asia. It doesn't help us locate it. Okay, is that all I said on that? Yeah, that's all I'm going to say on that. Estimated migration speed. But this is something fun we can do with ancient DNA, although it has its difficulties there. We can actually, this is a bit of a tangent. Without going into too much detail, trying to keep my time under control, with a certain pattern of ancient skeletons and SNPs, which I show on the left, if simple criteria are met, like site 2 here has both SNP1 and SNP2, and site 1 has SNP1, we can estimate the speed. We know the distance between these sites because we know the geography. We know the latitude and longitude of each skeleton. We know the dates thanks to carbon dating and SNP dating. So we can estimate the speed it must have taken, the minimum speed that it must have taken for this to occur. And we do that across all the available SNPs, mitochondrial and Y-DNA. And here's the speeds we get in kilometers per year. So you see all through the Paleolithic, Mesolithic, guess what? People are walking. That's all they can do. And although you can walk, 3 miles an hour or something on the average, this is net migration. So we're down in the realm of 0.2 kilometer a year, a couple hundred meters a year on average net migration. Now that doesn't mean you walk that much every year. Of course, you walk massively more. You're hunter-gatherers. But it means that your tribe might stay in the same place for a few generations, and then the food runs out, or the buffalo run away, or those other guys come over the hill and they're really scary. And then you pick up and you move, 50 miles. And this goes on and on for thousands of years, averaging a couple hundred meters a year. All of a sudden, now look in the Neolithic. We get farming, we get stability, everything picks up. And guess what? The Neolithic to late Neolithic, what do we discover? Horses. Now, I don't know if it's a glitch. There's a lot of error and averaging going on here, but it's intriguing that peak of blue, of Y-DNA in the late Neolithic could actually represent what you probably have all heard about, Yamnaya on horseback, men on horses. For the first time ever, we domesticate horses and can move much, much faster. And it's true, we'll show them later on. The migration speed here makes perfect sense. It's a lot of fun to get that out of the ancient DNA. Oh, by the way, there's other ancient DNA. It isn't limited to people. And this is where reading the archaeology literature helps, because the academics try to pull this together for you. People have done similar things, digging up ancient bones and sequencing for donkeys, domesticated donkeys, starting 2500 BC in the Fertile Crescent. And there are donkey bones, not my thing, but somebody's, that's good, all over the place. And you can see how they've moved hither and there. Horses, domestic horses. Of course, we ate horses for a while when we could catch them, but we domesticate them around 3500 BC in the steppes shown there, north of the Caspian and the Black Sea. And we have ancient horse remains going all over the place in both directions, as you can see. And we also do this for plague viruses. The Yersinia pestis, the origin of the Black Death, the earliest strain. Gee, we're all familiar with this from COVID, right? Remember all the COVID sequences that show us how it moves around the world? Same exact thing goes on here. And we can track Yersinia pestis primordial strains from 3700 BC, originating somewhere in Eastern Central Europe and going north and going east from there. So ancient DNA, all this adds up together. I've got references at the bottom. These slides will be posted by me and probably by Tim, or you'll have the video so you can check out the references later. All right, DNA ancestry, boogieing along. Remember map earlier with the blue blobs? Now we're going to go bronze to modern era, and we're down to about 600-mile average uncertainty. User ancestry, here's what it looks like typically. So if you have what's useful is when you have a SNP, I chose M222, which is a stereotypically Irish one, if you want to call it that. Sip of coffee. M222, we have 435 men at the current time who assert Irish male ancestry. We have 113 who assert Scottish, 41 American, 38 Northern Irish, 34 British, and 30 English. That's pretty clear. There's a very good majority of Irish and Irish plus Scottish, which are actually very close. You can see across the water, there's a lot of transfer, even in ancient times, between the two. Pretty good bet M222 originates in Ireland, or maybe you could even say Northern Ireland, based on the percentages of Scots and Northern Irish in there as well. On the other hand, there's a lot of SNPs. I just picked one at random, IFTT66, and that's what we got. First of all, they're very small numbers. There's no majority, and there's no pattern that we can understand. somebody asserts British, somebody asserts Spanish, somebody says US. You scratch your head, and that doesn't help me locate where FTT 66 first originated. It's just not useful. So you've got to take that into account. Now, here are a couple of examples where I think it looks it works rather nicely. Again, M222, I showed you before. We have 6,500 men have tested, M222 recorded for it. Majority Irish. It's a pretty good bet that that path I show you there ends up in Ireland to 222. Ireland, you could maybe debate about, Scotland or northwestern England, but that's not a big distance at all in the scheme of things. Similarly, I picked one again that's really extreme, 1,300 testers, which the Finns are bananas for DNA testing. Don't ask me why. Nothing else to do in the long, dark winters. Anyway, 1,300 Finns have this SNP NZ4998. It's so massively Finnish, and most of the rest are Swedish. It's a really good bet that's where it originated, or else we have to propose all kinds of odd migrations. So we can put the end of that long line across Eurasia pretty confidently in Finland on that basis. Testing bias. Well, I'm not going to tell you how you solve this. It's kind of a mess and some guesswork and simulation. But on the left, we have the distribution of 280,000 Y-DNA testers. This is the ancestries, paternal ancestries that men who've done Y-DNA testing assert. And now, UK doesn't mean you live in Britain. It means you assert that you have British ancestry. So I do, for example. I have a very good paper trail that puts my paternal ancestry in Britain. So I asserted UK in that part of the pie chart. And on and on and on you see. There's a massive European bias. US doesn't help us for reasons we may talk about later, mostly because our immigration jumbled up everything about the Y-DNA patterns. So that doesn't help us. Saudi is interesting. They're like the Finns. It's a very male-centric society. They got money. They're very interested in it. It's important. So the Saudis also test like crazy. That doesn't help us with too many patterns other than their own, of course. Anyway, it's massively Eurocentric compared to the world on the right. And you can see the same pie there. So this is why I drew that map before and said that the asserted ancestry is really only helpful in Europe, in Western Europe. There's also a problem of averaging. I get this now and then, and I kind of scratch my head and say, do I really have to tell you why this works? If somebody says Swedish ancestry and under the same SNP, and somebody says Swedish and an equal number say English, that actually doesn't mean your ancestor lived in the middle of the North Sea. Okay. It means it's one or the other, but we don't have the data to determine which. So I rather unapologetically, you could quibble with me about it, I put the dot in the middle of the North Sea, hoping that you'll kind of figure that's what that means. Another thing which is a little more harder to know because it's over land, if you have a Spanish mother and German father, that doesn't make you French. All right, it's kind of dumb, but this is part of the uncertainty that goes along with using user-asserted ancestry. Sometimes, like that majority Irish or majority Finnish case I showed you, it's really pretty clear. It doesn't take a lot of fancy math or averaging to figure out those are pretty confident locations for those SNPs. But in many other cases, this is why those error bars the error circles are the size of a country, because that's the data you get. Averaging and smoothing. I think this is the last one I have about this, a good example. On the lower right is what you'll get by default if you open up SNP Tracker and you ask for the path to, I think it's RFTA 81023. I just picked one that illustrated my point here. And you get a nice path that comes zooming in from the east, goes down to southern France, and then comes pretty much a straight line up into England. Okay. Look at the data. Why do you say that? Why would we say that? Look at the data on the left. Here's what the data I built that map from. And these are all the ancestries of the SNPs that on the map. The first row, DF27, you can see is Spanish, 29, England, 29, France, 17, Italy, 16, and so forth. Remember, there's a high Anglo bias, a lot of British bias. We're going to discount that 29, and that makes us pretty confident. DF27 is French and Spanish and Italian. Those are the ones that jump out when we take away the known bias of testing. So we can be pretty confident of putting DF27 somewhere around southern France. Leave that, it's a pretty good bet. There's other branching data why that's a good bet anyway. We look at the very bottom of that diagram and we get American doesn't help us and the rest are English and UK. So we can be pretty confident the bottom of this path is in Britain. In the middle, it's just a dog's breakfast of European assertions. I got everything under the sun there. I've got all kinds of nations in kind of numbers that aren't too dissimilar. And I can't say very much. That's why if I treat all these SNPs all along that path separately, I get the path in the middle, average by SNP. And if I don't combine anything, if I just leave it with by SNP, all that funky, messy averaging leads me to a ridiculous path that goes zooming up to England, back into Germany, and back over to England. It's kind of implausible. And the error circles in the dotted lines show it's massively within that one standard deviation error circle. And that's why I hide this. I smooth it. Some people hate smoothing in science. At some point in a case like this, I think it's justified because I don't want anybody to look at a map that zigzags all over the place, like the one in the middle there, and say, wow, my ancestors went from Brittany to Cornwall, and then they zoomed back into Alsace-Lorraine, and then they zoom back to England. No, there's no data to assert, or the data that asserts that is massively uncertain. It's much, all we can really say is what the simple map on the right says after smoothing, is you came in from the east, your ancestry went to southern France, northern Spain area, and then boogied up to Britain. And that's all you're really permitted to say by the data. So this is why averaging and smoothing. And in some other products, no names here, they don't do this, and you get some paths which I think are completely unjustified by the data. All right. So here's what I said. It takes a lot of calibration and weighting to reduce the bias, and we've got to smooth it out to reduce the noise. But we can't ignore it. Some people say, well, I don't like user data. They could be wrong. You say assert Spanish ancestry, it might be Portuguese, or it might be Italian. Well, you just got to go with the data you have, because there's 50 times more of this than there is ancient DNA. We can't afford to throw it out. We just have to use it carefully. Surnames and census. Okay, switching gears again. So hold on to your hat. This method is limited to Britain and Ireland because that's where we got the data. We have the census data. I have, thanks to some friends who lent it to me and scraping of websites, public websites and things, I have very good census data at the county level, not the town level, county level, for Britain and Ireland, from 1865 to 1880 for Ireland and 1881 for Britain, by which I mean Scotland, Wales, and England, not Northern Ireland. But anyway, that excludes most other countries. I just don't have the census data. And secondly, the important thing is surnames arose in the British Isles in situ, in place. The people were there, and then the Normans come in, 1066, right? And all that. The Normans come in. A couple of years, the Normans say, hey, we want to rationalize property ownership and taxation, so everybody's got to get a surname. So in a very short period of time, from 1100 to 1400, surnames are imposed on everybody in Britain and then pretty quickly in Ireland, that just freeze the geographic patterns that were there already. The people were there, and then surnames come popping in out of thin air onto them. And so that's the lovely thing about this, and that's preserved in the census data. That's, in one way of saying it, why you can't use this method in North America, because the people traveled there. I'm excluding, unfortunately, for lack of that, I'm excluding Native Americans. I'm talking about most of us who are immigrants. We came over with our names. And so everything got jumbled up. It doesn't show a pattern that pre-existed there that would caused by DNA migration, DNA measurable migrations. All right. So a couple of examples of using this. Let's go on the left, first of all. We'll pick a nice SNP, RYP326. If we look up the haplotree, we'll see that people have attached the surnames MacDonald, and McDonald to that SNP, meaning people who have that SNP many of them have those surnames. Well, that's on the haplotree. That's great. But now if we look up the census, now we map that to the census, we find that those names, and this is the map below, see the little pie charts? That shows the prevalence of those names, is really prevalent in the Highlands, and in particular, the Highlands up near Inverness, Inverary to Inverness in Scotland. So the surname, the SNP to surname to census data puts YP326 descendants in northern Scotland. Now, ZP2 in the middle is a more subtle case and a powerful case. If we look up men who have ZP2, we see the surnames Dunbar, Coburn, Preston, and Rutherford come up a lot, okay? And you think, well, okay. And if you look up those Dunbar, Coburn, Preston, Rutherford, which I've done on the various websites and the genealogy of these names, they're all separate. Amazingly, they don't seem to know this, which kind of boggles my mind. They don't read my websites. But seriously, they think it all kind of ends where the paper trail runs out, traditional genealogy. Oh, there's this old guy named Coburn in the Middle Ages, and we all descend from him. Well, that's true. But you all have ZP2. And if you look on the census maps of where those names are prevalent, whoa, look at the map in the middle. All those pie charts show you they're massively prevalent in the eastern Scottish borders of northeastern England and southeastern Scotland. Those names and the overlap is beyond coincidence. So that puts ZP2 in that part of what's called the eastern borders of Scotland, which is really interesting. And I hope some people named Dunbar, Coburn, Preston, Rutherford will forget about the surnames and follow the DNA, and they can take their ancestry back a lot further than they may have realized. And finally, on the right, I show something. I picked one at random. There can be any number that come up with a predominant Smith, FT27362, a lot of Smiths. Well, gee, Smith is a name, of course, because it means the Normans come into town and they look at this guy, and Big John is standing there with his hammer and his anvil. They say, John, what do you do? He says, well, I work iron. I make horseshoes. They said, good, your name is John Smith. You're a blacksmith. And that's exactly how it happens. Every village needed a blacksmith. And so Smith is all over the place, and it doesn't help us to locate at all. So again, you've got to use it with care. And sometimes you're lucky and sometimes you're unlucky. A little sidetrack here on surname localization, because I think it's fun. If I were to say to you, where do I find MAC and MC surnames? MacDonald, McDougall, McGregor, you'd say, oh, Scotland and Ireland, and that would be fine. And if I said, where do you find O'Leary, O'Donnell, O'Donoghue, you'd say, well, those are Irish. O names are Irish, and that's true. But let's look at some others. You can go a lot deeper than that. That's what's fun. When you have all the census data and you have the computer power to do it, you can find some interesting patterns. Now, here's a name. If I take Wilson, Johnson, Robinson, Thompson, Jackson, incredibly common names. And you think, well, there couldn't be any pattern with names like that. There is. SON is almost buried in the noise, but you can see it. It comes from the Old Norse. Hagarsson, Invarsson, Aigarsson, whatever. It's Norse. And of course, you know your early British history, the Danelaw, the Vikings, the pattern where you find those names today is a beautiful match for the parts of the British Isles that the Vikings controlled for hundreds of years. And gee, guess what? Just before the Normans come to town and stamp the name. Remember I said the Normans come to town and pop the names in out of thin air? The Viking, the Danelaw, well, and Normans, of course, were 5 generations descended from Vikings. You know that from Rollo the Viking. William the Conqueror's great-great-great-granddaddy was a Viking. So it's very soon thereafter that people are all hanging around, just living, doing their things in these villages. And they all have, it's all Viking stuff. So they get names like that. So that pattern is still very apparent today, the Norse patronymics. Fitzgerald, Fitzpatrick, Fitzsimmons, Fitzgibbon. If you said Irish, you'd be right, but it's more specific. It's actually Southern and Eastern Irish. Why? Because Fitz comes from the French fils, son of, and that was the name the Normans, again, a few generations after William the Conqueror, they started inserting aristocratic landlords for, cronies and favoritism and all that. They thanks Irish. They give them landed estates in Ireland to control. This is the Norse thing to do. And over there, they had the Irish feast, son of becomes Fitz. And so that's where you get those names, Southern Ireland, where those great estates were. Another interesting example, Kirby, Rigby, Ashby, Darby, Appleby, Selby, pretty common. B, as in by, as in near, is from the Anglo-Saxon word for near. And guess where all those names locate? Anglo-Saxon headquarters. When the Anglo-Saxons come in after the Romans leave, gee, where do they mostly settle? Where they land. And there you are in East Central England. That's where those names appear. And tree, as in Trevor, Treadwell, Trahoon, Traharn, others, is from a Cornish word for homestead. So if that more or less translates to farm, the Normans come in and says, "Who are you?" I'm Thomas and I live on that farm. Good. You're Thomas Trehue or whatever it is. So those are all Cornish names, TRE. So that gives you examples of both general and specific, how names can be, sometimes, if you're lucky, can be very, very powerful for localization. Okay, family tree location. A thing I haven't talked about before ever. And I haven't implemented, but I'll show you how it would work. Okay, 3 diagrams here. You're a DNA tester, and that's you on the far left. This guy down here, in the blue. And you've just done your big Y test, and you don't know anybody else who has, nobody around you has. So where did the SNP originate that you got? You got assigned a SNP. The answer is you don't know. It could have originated with you, meaning your father might not have had it, but you don't know. He hasn't tested it. You haven't tested your brother. You don't know. It could be with your grandfather. It could be much earlier. You don't know. In the first case on the left, you don't know where you know you have the SNP, but you don't know where it originated. In the second case, 2 first cousins test, and that's the dark blue. They're positive. Well, we know that their grandfather must have had it, and you can follow the diagram, you can figure it out. We know their fathers must have had it, grandfather must have had it, but we don't know it originated. It could have originated with their great-grandfather or great-great-grandfather or 5 or 6 back. But we know it's at least back that far. Now, here's the great case on the right. 2 brothers test, and they have a SNP. That's great. So it goes all the way up. Their father must have it, and their grandfather must have it. But no, it may not have it. Now, a first cousin tests, and he's negative. This is the clincher. The negative information is critical, because if he's negative, it means his father and grandfather can't have it, because SNPs are always passed down, father to son. That means grandpa didn't have it, but father did, so it must have originated with the father there in the yellow star. He's the proven originator of that SNP. So you've got to have positive evidence, and you've got to have a brother relationship with negative evidence. And then you can locate the origin, where that SNP occurred exactly. So how does that work for geography? Well, here's the best I can do to come up with, or rather the earliest. And of course it has to do with kings and aristocrats, because they're the ones who preserve the data, and genealogy is the best. So we happen to have this case. John Stuart of Bonkill. I don't know if I'd like that name in history. John of Bonkill, born around 1246. Well, he has 2 sons, Alan and James. He has other sons, but 2, Alan and James. And we know from good paper trails, remember, these are aristocrats, so they preserve all this stuff because it matters who inherits the house and the land and the name and all that stuff. One of them goes down through King of England, Scotland, England. James VI is James I. And so they all know who they are on the paper trail, and they all have RS781. They have that SNP, okay? So, but here's critically, John's brother, James, who's the 5th High Steward of Scotland, blah, 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 down through Robert II, another king. So we got all the data. Everybody wants to be descended from a king. So they pay attention to it, but they don't have it. They don't have 781. That means that RS 781 had to have originated literally in John Stuart of Bonkill, born around 1246. So if we want to put that on, the funny part is about this example is that the genealogy and the DNA is great. The funny thing is we don't know exactly when he was born, and we don't know exactly where. Best guess, this is a Victorian folly, a faux castle built by the Victorians, but probably on the site of an earlier castle, which may have been where he was born in 1246. So we'll take that as a given. It's the best we can do. The point being, as far as locating a SNP on a map, we can nail this down. Exact year, well, as far as we know for him personally, the year and the location within a few yards of where the guy was born. So that's the best we could ever possibly do, which is really rather cool. Methods. Wow, I'm going to go over the hour. Okay, speed up. Now it gets fun. Connect the dots. Well, this is probably self-evident. If you know that, let's say you have RDC782, you look up all the SNPs you have all the others. We can go back in time. L23, M207, and AAPR2921. You have all those because we have all the ones our fathers and grandfathers had. We also know from ancient DNA where they were, where there were examples of that, and where they're probably located. So all we have to do is connect the dots, thanks to the haplotree, gives us a sequence. Connect the sequence in time, and already, just from ancient DNA, the broad strokes of migration are mapped out for us. Again, this is as good as it was, I don't know, 10 or 15 years ago in National Geographic or a textbook of ancient people, the migrations of ancient people. And you can get that just from connecting the ancient DNA dots. Branching geometry. This is actually a big deal. I kind of do this not by computer so much, but just by looking at it, and if you want to call it common sense. We know from the branching of the haplotree that haplogroup F has branches going in all directions as shown, G, J2, P, Q, R, and H. We know it came out of Africa, across Arabia, get to that. And how it's got to be, F has to be stable for a while for all that branching to occur. It can't be nomads who move along every 10 or 15 years or something. So it has to be in a nice livable place. And then it has to be at a crossroads in all directions. And the only answer that kind of makes sense is Mesopotamia. It isn't called the Fertile Crescent for nothing. So it's pretty good bet that the branching alone of all its descendants puts F there in the Fertile Crescent or pretty close to it. 2-point interpolation. We get into a little math here, and I'm going to skip the 3-point. Let's say that we have 2 SNPs that we know, the blue ones there. Let's say we know where one is on the right, L1026, at a certain date and a known location, and then one on the left, Z1233. We also know its time and date. But what we want to do is locate all the ones in the middle if we don't have any data for them. Well, if we assume minimum effort, that means the location of all those SNPs in between have to be on a straight line between them. I mean, that's an argument from parsimony. That's Occam's razor argument. The simplest thing is probably right. It's not proof, but that's the best we can do. So location is on a line between the endpoints. And then we assume constant travel speed. Remember that diagram I showed you about inferred travel speed? It was pretty constant on average. Of course, there are exceptions, but on average, from the Paleolithic, Mesolithic up until the Neolithic, it was pretty steady at like 1/3 of a kilometer per year. So if you assume constant travel speed, then the distances are proportional to the time, and we can locate, shown by the yellow arrow on the bottom, and all the other SNPs in that line, for which we don't have any branching data. We can guess, educated guess, interpolation, where they probably were located when they occurred. That's 2-point interpolation. I'm going to skip this. 3-point is more complex. The math gets lots of fun. It's a more difficult problem, but needless to say, in many cases, it can be done. Negative evidence. This is worth a thought. How's everybody's head filling up here? Good. A thing to think about, the Nile Delta in the dotted circle there, the Nile Delta and the Levant, modern Palestine and all that, are habitable. They have been for many millennia, and they're host to all kinds of other DNA branches and pathways that aren't shown on this simplified map. We know that people have lived there for a long time, crisscrossing all over the place, and the ancient donkeys went through there and so forth and so on. It's a nice place to live, okay? But if you look from C to F, now I'm using the simple names here, C1 to F1 if you want to get that picky. If you look from C to F, there aren't any branches up there. There's no descendants in the right time frame from C to F are in the Nile Delta or the Levant. Now that's pretty curious because you'd expect there to be, spilling. This would take thousands of years to get there from one place to the other. You'd think that spin off people would stop and say, hey, it's really nice up here in the Nile. The fishing's pretty good. The other people here are nice. I'm going to stay. And you'd get a marker in the Nile Delta. You don't. So it's negative evidence. So given that you have a choice out of Africa of the southern route shown in green and the northern route, the negative evidence argues for the southern route. Actually, we do have some archaeology. There are some skulls and flint tools flint tools at least, in the right place here along the southern boundary of Arabia. And we don't have DNA from them, but we do know that Homo sapiens of about the right age was in that region. So it's perfectly plausible that people were there. We also know that when there are ice ages, the sea level was lower, that you could walk across the straits at the end of the Red Sea. So it's perfectly reasonable to suppose this northern or southern route. The negative evidence suggests the southern route. It's controversial, but you got to make a choice when you're drawing a map. So that's why I make the choice. Here's one where I disagree with some of the other folks who do the mapping. And here's one of the big pieces of why I disagree. There are the red arrow here. R1b is the most prevalent marker of European descended males. Not me, but a lot of others. And most maps will draw R1b coming over the steppes, coming over from Eurasia, as shown here in this light red arrow. Okay, I don't think they're thinking too much. Here's why. R1a, which is prevalent today and in ancient DNA up toward Latvia, Estonia, Lithuania, Sweden, northern Poland, and Germany. R1a is also a steppe, Yamnaya steppe, early Bronze Age marker. And they both originate, of course, in R. The haplotree tells us this. So they split across in R. Now, if they had spent 1,000 years going across the steppe, learning how to make bronze, learning to domesticate horses together, you would think that they would mix. You would think that the R1a would be a mixed bag. Let's say that'd be mixed or whatever the population. Remember, markers are invisible. Until you can sequence DNA, you can't see a marker. They don't code for anything. Y-DNA doesn't code for anything, not hair color, height, skin color, nothing. They're invisible markers. That's why they're good for us, because they're unbiased. So you'd think that R1a would be 30% R1b, and over here you'd also have the same mix. Well, because they had 1,000 years to mix it up, but they don't. They're very separate. These are until 1,000 years later, in later Bronze Age, now these R1a and R1b are well mixed in Denmark and the Low Countries in France and Britain. Well, that's fine. But at this early point, they're not mixed. So they had to split. Well, where can you split? The only place you can really split is to go south of the Caspian. Does that seem like a long way around? Well, it does, but that's us being silly looking at a map. And if you're a hunter-gatherer in the Paleolithic, as you were in R1, and you got to move, let's say the climate changes on you or the bad guys come over the hill and you got to move, all you can see is 20, 30, 40 miles ahead. And you can't see the Caspian Sea ahead of you. You're already committed. What are you doing? You're following animal tracks. You're following where those things you like to eat with that certain hoof print, and your expert trackers, your hunter-gatherers, you depend on it. You pass this knowledge. You're just as smart as we are. You pass down this knowledge. That animal trail goes along there, and this is a known trail. The Indus corridor, whatever, I forget what it's called now. And you follow them along, and some other guys follow some other animal tracks, and pretty soon you know these markers are split apart. So there's good negative evidence here. Why these had to split early, and the simplest place to do it, and there's some other reason about branching and acquiring of arsenical bronze that argue for R1b taking that path that I show. Summarizing data sources. Ancient DNA gives us a broad outlines of ancient migrations. User Ancestry gives us post-Roman locations with nation-scale accuracy, especially Western Europe. Surnames and census data look at Anglo-Irish post-medieval SNPs with county-scale accuracy, if you're lucky and you aren't named Smith. And occasionally, if you have traditional genealogy with that tight set of criteria about yes brother, no cousin, you can locate recent SNPs precisely. Problems. Okay, bad ancient data. And this annoys me. What can I say? You will find maps, not me, not mine, that put IM253 in Spain. All right. And that's on the basis of 2 ancient samples found in Spain. You can look up the literature. I could get you the references if you wanted. Trouble is the radiocarbon for one of these samples is 22,000 BC, and the radiocarbon for the other is 11,000 BC. Here's the problem. That marker arose in 2600 BC. They couldn't have the marker. It didn't exist for thousands and thousands of years. The academics are wrong. I'm not saying it's deliberate. It might have been contamination with modern DNA. I don't know what, but those 2 samples are wrong, are misdated in the literature, and they haven't been corrected. And it's silly. It's also, there's another thing, all M253's modern descendants are all Northern European. There's nobody south of Germany. So this is an error that jumps out at you. It's easy to find by the math, by the dates. People preserve it, people don't question it. And you get terrible maps that show doing this red route from Austria area down to Spain and up to become Vikings. And you get junk, I have to say, like Facebook forums that say, oh, the Vikings were Spanish. And I say, oh my God, come on. Can we just look at the data sometime and make a little critical judgment about it? Because the dates, this is a pretty easy one to spot. Weird round trip. You know what? This is an interesting story, but it's complicated. If you want to get into in the questions, let's do that. Weird round trip is a problem of a certain vendor who makes maps that people take to be very precise. And they make a big problem all the time on what I can call naive tagging. And this is just an example. Maybe I'll go into it if you want. But a lot of the details of maps you'll find from a certain vendor are full of basically really bad paths that, if you think about it a little bit and you look at the data, don't make any sense at all. And I don't know what we can ever do to correct them, but it's frustrating. All right, let's get to some interesting observations. Now, this has nothing to do with mapping, although the implications for mapping are rather interesting. Paper came out in 2015 from the Mark Joblin group with a remarkable assertion. 2/3 of European men are descended from just 3 men. Get that? 2/3 of all European men and men of European descent, like me, male descent, are descended from just 3 guys. Those 3 guys all lived in the late Neolithic to late Neolithic, more or less. And here's, roughly speaking, where their markers are. They could be a little bit west of there for the blue ones. I'm not going to worry about it exactly. But we would call these in broad brush R1A, R1B, and I1A. This has a huge, guess why Y chromosome stuff works well in Western Europe? Here's why, because it's simpler. Women didn't go through these genetic bottlenecks, and they have much higher DNA diversity. That's very interesting. It's also one of the reasons, along with the 7,000-year gap, why inferring locations from mtDNA is quite a bit harder. If you have one of these male markers here, you're basically Western Europe. You know, I got half the job done in mapping just knowing that, because you all descended from just 3 men. Remarkable. It says a whole lot about culture, about Neolithic culture, that can honestly get kind of creepy like Genghis Khan or Saudi king creepy. You can talk about that if you want. Migration speeds. Remember I showed you the speeds before, inferred speeds? Well, we can do that between any 2 SNPs on a map. We can put it on the map because we know the dates and we know the locations. Therefore, we can compute the velocity. That's just real simple physics. And when you do that and you color it, here's what you get. And these are all the major paths of Y-DNA. Now, they're mostly blue, and that's all that Paleolithic, between less than 1 kilometer per year on average. You can see coming out of Africa, going up the Arabian Peninsulas, other lines like mine went up the Nile, come around through Europe. We're walking. We're walking the whole time. We're walking out to Mongolia. We're walking back. What's really interesting here is with the red. Both these red segments from L23 to L51, and this from Z93, Z94, originate in the same area at the same time. What's going on? Horses. This is the domestication of horses. And these are the nomadic steppe people. These are the Yamnaya. It tells us they had horses, and it tells us they used them. They didn't sit there and scratch farm. They could have scratch farmed. They didn't sit there and work their herds of goats and sheep. They rode. They were nomadic, and it shows up in the distance between the SNP markers that their ancient bones left in the dust. And we can pick it up. Very simple calculation. So it's fascinating to me. All of a sudden, we're walking. We domesticate horses, bam, we take off from half kilometer a year to more than 4 kilometers a year. We are boogieing. And that kind of persists here in what? Until they run into the ocean. And that's Yamnaya. If you know, the steppe people took the, now called the beaker, to the corded ware, and then the beaker culture completely overran, completely replaced the DNA of all of Western Europe. We have Iberia, all of Britain, and a very recent study, all of Denmark. They took the whole thing. They overturned it, basically 90+% of the DNA, and they were moving until they hit the ocean. An incredible story. Oh, why SNP examples of autosomal migrations? Academics don't deal with Y and mtDNA much anymore because now they can do whole DNA sequencing. And face it, if you thought 20 million base pairs was good for the Y chromosome, try 3 billion if you do the whole genome. Simply put, there's just a whole lot more data there. Why wouldn't you do it? So everything you see in the literature now, and there are papers, I get Science and Nature, and there's almost every week, there's something about ancient DNA or related to ancient DNA, certainly every month, a major paper. This is a summary map from David Reich's book, Who We Are and How We Got Here, highly recommended. And his map is in black and white, and I put in the red. He draws based on autosomal DNA, where he's one of the world experts. His lab are superb. What his view of the mapping, this is based on ancient DNA, whole genome sequencing of how, let's say, number 2 here. No, so let's start with 1. This is the Neolithic Revolution. This is where people come out of the Fertile Crescent down here in Mesopotamia. They come across Anatolia, ancient Turkey, and this is what defines the Neolithic. The difference between the Meso and Neolithic is when these folks in Europe, these folks cross into Europe and spread the knowledge of farming, and they bring their goats and sheep with them, and their early millet and so forth. Well, we can assign Y SNPs to them. It doesn't mean it's exhaustive. Not everybody who was an Anatolian agriculturalist had this J or G or E marker. And on the other side, they didn't all have EV13, which I have, or GL166, but some did. And that's fun because we can get a little more specific. We can attach specific markers to some of the people. You get the idea. Here, Iranian agriculture spreads east. Some of these people were HM52s. Some that took this northern route were JM172s. Some of the Yamnaya pastoralists, probably a lot actually, are Z93. Remember I talked about that, here it is, the Inter-Asian Mountain Corridor. They're using it much later, probably for the same reason the Paleolithic people did it earlier on, because the animals before them for millions of years trudged up and down because they just found those paths because they could survive. There was water, there was stuff to graze on, and so forth and so on. People later follow animal tracks, that becomes a path, that becomes a highway. Here they're Yamnaya using the same thing in their horses going into India. Okay, so we can match up with reasonable some guesswork, but reasonable, the literature, the academic literature on autosomal migrations with some of our Y markers. Going around barriers, I'm getting to the end here. I want to leave plenty of time for questions and all. Some of what I've talked about here was about getting around barriers. I made a point before. Let me have some coffee. I made a point before about R1A and R1B splitting around the Caspian Sea because of some negative evidence that they didn't mix, which is all true. There's some other splittings and branchings that suggest that also makes a lot of sense. But here's the point. The Caspian Sea is a barrier. It certainly was in the Mesolithic. You could, I don't know if you can see across it. Maybe from the mountains you can on a really good day. But basically it's a Great Lake. You can't see across from shore level. You're not getting across it. Your boats are hollowed out logs. You're not going across it. It's a barrier. The best air barrier in the world, obviously, are the Himalayas and Tibet. If you're coming out of F and you're branching out and you're following those animal tracks, one guy goes this way, his brother goes that way. These end up giving rise to haplogroups N and P. After a while, you're not crossing Tibet. The paths have to go around it. There's no other way. Some really bad maps show going right across. I'm sorry, you didn't follow an animal track up over the Himalayas. It just doesn't make sense. Out of Africa, I described that one before. You have two plausible routes, especially with the Ice Age when the sea level was lower, and you could walk across the straits there of the Red Sea. You could cross above or below the Red Sea, which is a barrier. The Saudi Desert, although at one point it was greenish, it wasn't then. That's a barrier. You've got to get around it. And everywhere there's Mediterranean's obviously a barrier. Everywhere there's a barrier, you can find examples of people who went around one way or the other. Meaning, unlike those textbook maps, maybe in the 1960s or 70s that have one big whacking arrow. No, you can find examples, and you can put haplogroups on them. You can put SNPs on them. For people just wandered all over the place. Most of them died. They got one way or another. They got around the Carpathians, got around the Alps. You can find examples going any which way you want. And the fun thing is, some of them, like the three guys I mentioned about at the outset from Isle of Man, sometimes it was your daddy's and somebody else's daddy took different routes around those barriers. And that's all it was. Okay, this is about the end here. Now, North America, it's not on SNP Tracker. Big reason why is we don't have the data. Like I said, we brought our SNPs with us. Pick anything you want. Pick Irish. Well, some Irish with M222 landed in Boston, others landed in Philadelphia, others landed in Virginia. and then they moved all over the place really quickly. There's no pattern to M222 anymore. And the same goes for everything in Y-DNA, with maybe some very rare exceptions. However, there's a really interesting paper I referenced at the bottom. I really wish they'd follow up on this, but they haven't as far as I've seen. 2017. This is by the people at Ancestry DNA, who have a unique set of data, much bigger now than it was then. They have 700,000 DNA samples at that point, ancestry or autosomal samples, and they had 500,000 curated family trees from the other half of the company, just called Ancestry. Now, a lot of those trees have errors, but they have a lot of clever computer stuff to clean out most of those errors. They curated them ferociously because they have so much data. When you boil that together, it's very clever computer and math work. You can see North American migrations of immigrants at a huge scale in autosomal DNA. It's quite sophisticated without going into methods and all. It's not Y-DNA now. That turns out to be a jumble, but you can see the pattern in the autosomal, which is very, very clever. So we have a northeast in Utah of all the curious things. Similar, well, it's obviously Mormons moving out, but here we have your Northeasterners. We have Pennsylvania. If you want to call this Pennsylvania Dutch, et cetera, that would be fair. And they move west. We have another branch, a lot of the red here going across the Appalachians, and down here would be so-called Ulster Scots or Scotch Irish, or a lot of these. 500,000 people, so half that number of men, come over between the Tudor, the Stuarts doing nasty things, James the First, et cetera, doing nasty things, clobbering Northern Ireland with poor Scots and poor English in the early 1600s. That was called the plantations. And then later, a couple of generations later, expanding those things and kicking them out again, half of them out again, when they could get to North America. We have 500,000 people come over from Northern Ireland, and they largely end up, and the DNA is very traceable here, into down the Appalachians, into the Midwest, and so forth and so on. Upland South, African DNA jumps out a mile. You can see African DNA patterns, because they're so ancient, are very, very distinct, and that tracks exactly with some of the European DNA. Very, very easy to track and characteristic. And we have other interesting ones: Acadians, New Mexicans, Mexican groups, Portuguese. You can track with this method. Very interesting paper. Really neat to see North American patterns, but I can't do it with Y-DNA. All right, and here's my own to-do list. This is my hobby in retirement. So I've got to keep up with the haplotree growth and keep up with ancient DNA discoveries kind of all the time. I update my trees. FTDNA, of course, does this on an automated basis. They're the single biggest vendor. I update my trees from them about every 2 to 3 weeks. That's not so hard. I have it pretty automated. Ancient DNA, Carlos Quayle is a wonderful fellow I've met online, very brilliant. He's a surgeon. He's an orthopedic surgeon in Spain, and he's young. He's just started a family. So somehow this guy finds time and brilliance to be one of the best authors and students of ancient DNA anywhere. But he's gotten so busy now with his growing family and his medical practice. He's published this too. He's not just an MD. He's a research physician. Awesome, apparent, amazing guy, MD, PhD. But he has a wonderful database, best DNA database of ancient DNA. The Reich Lab does also. So I update from them every few months. What I haven't done is I don't show paths for the Americas, Africa, Pacific. I should do that, I suppose. I don't have modern data, but there is enough ancient data you could show it, at least for academic completeness. It's getting better and better all the time. It's all driven by ancient DNA and occasional modern testing, but not the sort of people who mail a swab into Houston. But when academics go out, they solicit modern people with legal agreements to do so. It's all pretty ethical. But we're learning more and more about the paths in the Americas, North and South, Africa, and the Pacific. I could improve barrier avoidance, meaning I really shouldn't put those dots in the North Sea. I know how to do it, but it's a lot of computer work, and I haven't gotten around to it. I could also integrate my methods across tools. I write those tools at different times. In an ideal world, I would integrate the surname and census data more completely with the Y-DNA data and the ancient other DNA data. and make that smoother. At the moment, my tools are rather separate. And a fairly new idea is it would be rather interesting to do, I may explore this next, include family tree paths from WikiTree. Remember I showed you about John Stewart of Balkill, and that curiosity, you could simplify that case with a few assumptions, and it would be rather interesting to go online interrogation of WikiTree. I may experiment with that. It might be possible to do some precise recent location of recent SNPs. We'll see.